Yeah, thanks everyone for joining. I'm talking, like Johannes said, a bit about compression for neural networks, and this time it's really compression. It's not quantization, pruning, it's compression in the classical sense. Maybe a bit different than what people are used to. This work has been done by me a year ago, so it's maybe not cutting edge. Please um, excuse this, but yeah, otherwise, let's get started. So our method is called Servo. This is a very catchy name. Compression with entropy regularized weight updates. And the problem setting that we have or that we want to solve is of course, that models are huge. Even like the simple ResNets are hundreds of megabytes uncompressed. At the time when I was working, these 1 billion models were already huge. Now it's 120 billion, so it's only getting bigger. Then we want to deploy this, for example, on edge devices. We can imagine parking sensors or something, and these are very small. They have tiny storage, they have tiny bandwidth, so they don't like big models. And why do we even want to use this on edge devices? We can also query the OpenAI server. Is of course, sometimes you want to have privacy, sometimes latency is important. Maybe the parking sensor does not want to have internet connection all the time. So on-device inference is of course very important. So our goal here was to shrink the stored model size with minimal accuracy loss. And here the focus is on shrinking stored model size. So it's not just quantization. We even argue that quantization is not equal to compression, which is in literature often a bit confused, because quantization is essentially storing weights at fixed bit sizes. So 4 or 8 bits are quite frequently used because it aligns nice with how your GPU processes data. They're usually great for inference speeds, but it wastes bits on easy to predict weights. And here compression can help. We can achieve this by adding entropy coding to quantization. And compression has as a goal to minimize the total bit string length, usually doing entropy coding. As a result, the effective bit width then varies per weight. You can even have an average bit width of 0.5 bits per weight, which is not achievable with normal quantization. And we can get better compression because we can use fewer bits for more predictable weights. Yeah. So maybe not everyone remembers entropy coding or vaguely remembers it from their information theory 101 course. So I have a short recap slide here. What entropy coding does is essentially the key idea is that we assign shorter bit strings to frequent symbols and longer bit strings to more rare symbols. So step one of entropy coding is that you build a probability model. With weights, we know they're like kind of normally distributed. So we can, for example, assume a probability model that assigns larger probabilities to the value 0 and then decays to both sides. Using this probability model, you then, in step 2, assign bit strings to the values. So you want to assign, of course, the shortest bit strings to the most frequent symbols. So the weight value 0 might get the code 0. The weight value -1 gets 100, +1 gets 101, and so on and so on. This will on average make some bit strings shorter and make some bit strings longer, but because the frequent symbols have short bit strings, you will on average save space. So the third step is then to compress the data. If we have this example tensor 0, 0, 1, 0, -1, 0, 0, if you want to naively store this with a fixed bit storage, you have to do something like in the orange box. So each weight gets 3 bits. This takes on average 24 bits. This is quite wasteful. If you use the assignment scheme that we have here, then you use only 12 bits because you can encode all these 0 values with just 1 bit, and the more frequent ones then with 3. And then you just hope that you have not a mismatch in your entropy model, because if you would encounter a lot of +2s, then you could also have longer bits, a longer total string, right? So it's really always important that this model predicting the data well. Okay, so the key insight that we had is, of course, if you naively do this, you could first quantize your weights and then you can entropy code them. The problem is that sometimes we might have some weights that are large in value. I don't know. They maybe take the value 10 or something, but they don't contribute much to the model accuracy. And ideally, we want to know this while quantizing. Then we could just set these unimportant weights to 0. Let's assume this is a cheap bit string. And the important weights we could preserve better. So what we were trying to do in our paper was using the idea that we want to use entropy coding later already during quantization to produce the representation that is most optimally compressible. So what we did was we want to jointly optimize for accuracy and bitrate. So instead of what you usually do during quantization is where you just minimize this objective. You take the weights and try to minimize the distance of the quantized weights to the original weights. We add this little objective term here that contains the information content, so the bits per weight that you need for the compressed weight representation. So by optimizing this objective, we can get a more compressible representation. So in our method, we have 3 key steps. The first one is usually this bit rate term, R of W hat. This is quite complicated. So we replaced it by a quadratic rate estimation. You can just assume a Gaussian weight distribution. This makes the objective tractable later. In the second step, we then change the quantizer. So it is actually, it's aware of the quantization. It's a bit of a difficult equation, but essentially, this step, this Q of Wij, assigns the quantized bit representation to a singular weight. So not to the whole weight tensor. So this is this thing that operates on each single weight. And what we want to do is we want to iterate over a grid of fixed values. In the end, we still need discrete weight representations. And we try to find the grid representational value that has a short distortion. So it's close to the original weight. And we weigh this by the inverse of the Hessian to assign some sort of sensitivity to it. And then we penalize this by the expected rate that we would have of this grid point. So that we can also take this into account, how much bits we pay for the weight tensor at each of the quantization steps. And third, we correct the remaining weights after each quantization step. So you can imagine if you take a weight tensor and you quantize a weight somewhere, you can correct the error you introduce by changing all of the other weights a tiny bit, and then you can continue and just greedily quantize these weights. Okay, and here's some nice results. The orange one is basically state-of-the-art, implemented in some ISO standard, state-of-the-art norm storage, optimal weight compression. And green is our proposed method. We tested lots of computer vision networks. Sadly, didn't work as well on transformers. But on average, we get something like 30 to 40% smaller file sizes. I think especially crazy, it's on some networks that are, of course, way over parameterized. But here you get, for example, 0.45 bits on VGG16, which is huge. Like if you would just try normal quantization for 4 bits, this file size would be just 10 times as small as a vanilla quantization algorithm. Okay. So yeah, maybe some practical performance information, what I find quite cool. It's quite fast to decompress. So you need sub 1 seconds to decompress. It's quite important that you decompress your weights faster than you compress them. Compressing is done once, usually decompressing is done many times. We achieve on average 20 to 40% smaller file sizes. We have a good adaptability because the quantization grid and the entropy models are treated as black boxes. They are freely choosable. And we achieve a smooth RD trade-off. So if you quantize, you can only choose the quantization bit width in discrete sizes. And here it's really smooth. So the lambda parameter that trades off accuracy and compression is a real value. You can set this to anywhere you want. And you can really choose what you need for your application. Yeah. Some of the limitations we didn't work. It didn't work. We tried on transformers. We think that has something to do with the transformers having different activation statistics. So some more work would be needed there. And then one thing is that encoding can be slow for large grids because you go over each of the grid points. There could be maybe some optimizations, for example, early stopping that would be helpful there, or a more targeted exploration of the grid. And future work I would be interested in is one thing that could be really cool is on-the-fly GPU decompression. Because in LLMs, for example, the inference is usually memory bound. So if you have small file sizes, if you have a small storage space, you could leverage this to get a faster inference speed because you can get the data into the GPU faster. This would, of course, require a very fast decoder. And the problem is that the decoder for entropy coding is usually not parallelizable. So this could be something interesting to do. And of course, exploring different entropy models or grids, how they work together with this method. Maybe something that works better on transformers would be nice. So yeah, some things to explore. Okay. Would be happy to hear any questions you have, and thanks for listening.